Okay, this video is going to be a follow-up to yesterday's video on mechanical efficiency. We're going to be looking at mechanical efficiency today and solving some problems, given some real-world examples of how machines work. So in order to get started, I'm going to just quickly show you in Schoology, 2020 students, when you go in today, you're going to click on the folder for week 8. And then you're going to click on the folder for 12/15, which is today. And in there, there's going to be actually more in there. This video will be in there once I get done with it. But that's the PDF file, Mechanical Efficiency PDF. And you're going to download that to Notability. And we're going to be working on that today. That eventually is going to be submitted to an assignment that's going to be entitled Mechanical Efficiency. You need to submit the notes and the solutions to the problems on that PDF. So we're going to look at that. So let's go into Notability. I already have that file in my Notability. Okay, here it is up top. It's entitled Mechanical Efficiency, or I titled it that. And you can do the same. And it looks like this. Okay. So again, if you did not watch yesterday's video, which is going to be in Monday's folder 12/14, please do so prior to watching this. If you have already watched Monday's video, we'll get started. So, yesterday we talked about this concept called mechanical efficiency, right? Mechanical efficiency is comparing work that is done by a machine to the work that the machine does to an object, right? So, we can define mechanical efficiency as, let me get my pencil, comparison of the work input to the work output of a machine. Okay, and just to give an example, a little stick figure physics here. I'll do the best I can. Let's say here is a person with a lever. Okay, and they are lifting I'm going to make my lever a little longer there. They're lifting an object over here. So this person is going to apply a force to this lever here. Okay, and they are going to move the lever on their end a certain distance, right? Those two things multiplied together are going to equal what's known as your work input on the lever. Okay, what the user of the machine does to the machine. On the other side, the lever is going to apply a force, and it's going to move this rock a certain distance over here. So once again, force and distance is work, but this work over here is going to be called our work output. Okay, we learned yesterday that there's always a small amount of friction in the use of a machine. So this lever, rubbing on the fulcrum in this area right here is going to reduce some of the work input. And so the work output always has to be less than the work input. You never do less work by using a machine. You always actually do more. However, since the work is made easier, machines are useful. Anyhow, mechanical efficiency is the comparison of those two things. How good is the machine at converting work input to work output? Okay, the formula for mechanical efficiency is ME, mechanical efficiency, is equal to work output, whoa, over work input, we, times 100. And the reason why it's times 100 is because mechanical efficiency is expressed as a percentage or a percent, right? Which is an expression related to 100. So if I have a 75% efficient machine, that means 75 hundredths of what I put in, I get out, more or less. I'm sure you guys have worked with percents a bit in math class, so you should be somewhat familiar with those. Okay, so we'll get into some problems with mechanical efficiency. A couple other things about machine. So I'm going to read number one down here. Although machines may provide a mechanical advantage, which is actually our lesson for tomorrow, but that's the way they make work easier. They actually always require the user to do more work, not less. Remember that. Use a machine, you do more work. Okay, whenever there's an increase in the force provided by a machine, so sometimes a machine can make us stronger, for number two here, but what happens is there's also an increase in distance over which the force has to be applied. So therefore, again, force times distance. Sometimes a machine can increase my force, but when it does so, it comes with a cost, and the cost is distance. I am going to have to move the machine a much greater distance on my end if I'm getting any increase in the force that I'm applying. So the amount of work input on the machine equals the work output in this case. Okay, an ideal machine. So we'll talk about what are known as ideal machines. These are machines which live in an imaginary world where there is no friction. And sometimes it's useful for us to discuss machines in this way. Okay. So in these ideal machines that we may encounter in our discussion, they are machines where the work input equals the work output, right? So up here, back to my guy with the lever, you've got equal amounts of work on both sides of the lever, the person on the lever and the lever on the rock. So this is a situation that the mechanical efficiency would actually be equal to 100% in these ideal machines. They don't exist, right? In the real world, the ME is always less than 100%. And the reason why, again, is because there's friction somewhere, and that friction causes work output to be lower than work input. It's always going to remove some of that energy, and then you end up with a reduction in work. Okay, so there's the notes, and these are required, right? When you turn this in, I'd like to see the fact that you paid attention to this and took these notes down. All right, next page. This doesn't look good, right? This looks like problems. All right, we're going to do some of these mechanical efficiency problems. So let's start with reading right here, this paragraph. It says the amount of work obtained from a machine is always less than the amount of work put into it. This is because some of the work is lost due to friction. The efficiency of a machine can be calculated using the following formula. Right now in the box, they're calling it percent efficiency. This is what I'm calling mechanical efficiency. Okay, just so you know, it's the same thing. Equals work output divided by work input times 100. Okay, so let's look at the first word problem. It says, what is the efficiency of the following machines? Number one, a man expends 100 joules of work to move a box up an inclined plane. The amount of work produced is 80 joules, right? So I'm going to do these problems. Remember how we did write all our variables over here? So I'm going to write ME, WO, WO, and WI. Okay. Now, this problem is pretty direct. It gives us the work. Let's think about what it says. A man expends 100 joules of work to move a box up an incline plane. The amount of work produced is 80 joules. Think about what the work being done by the user of the machine does. So what the man who is using the machine expends is our work input. So I'm going to fill in 100 joules down here by WI. Okay, the amount of work produced, which I guess is just getting the box up that particular height, is equal to 80 joules, which is my work output. Okay, so I'm going to set up my formula, ME equals WO over WI times 100 equals 80 divided by 100 times 100, which is equal to, if you take out your calculator and do your problem, 80%. Okay, and we would say that the mechanical efficiency of the machine in that problem is 80%. You get 80% of the work out that you put in. Okay, let's go down to number 2. Again, we're going to start with, whoops, let me get my eraser. ME, WO, WI. Work input, work output. Okay, and I wish they gave us a little more space to work on this worksheet, but it's pretty tight, so we're going to have to do the best we can. Now, let's read this problem. It says a box weighing 100 newtons is pushed up an incline plane that is 5 meters long. It takes a force of 75 newtons to push it to the top, which has a height of 3 meters. Okay, what's going on here? This one's not as easy as the last one, right? In the last one, we were given joules of work, input and output. And all we had to do was punch those numbers in and solve for mechanical efficiency. With this problem now, we're not given work directly, but what we are given is forces and distances. And guess what we can do with those? We can calculate work. So what I like to do with these problems is to visualize what's going on, is draw, sketch. So I'm going to go down here onto this blank section, right? And I'm going to try to do a sketch of what we have here. So I'm going to write down problem 2. And I've got a problem with an incline plane, which also known as a ramp. I'll draw it the best I can. I'm going to go back up here. A box weighing 100 newtons is pushed up a plane that is 5 meters long. Okay, so this is 5 meters. The length of this ramp from here to here. The box that's being pushed up, it weighs 100 newtons. Well, you know what? I probably should put that there. Right there. Uh-oh, I lost my incline plane too. I have to go back and put it back in. All right, let me read that again. Box weighs 100 newtons, pushed up an incline plane that is 5 meters long. It takes a force of 75 newtons to push it to the top, which has a height of 3 meters. So what it says is, here's my box. All right, and here's my person, pushing it up the ramp. It's amazing how he does that without his hands touching it. But it says that this person has to push with a force of 75 newtons. Okay? Whereas what actually happens is the box weighs 100 newtons and it is being lifted a distance of 3 meters. Okay? So what I have in this problem is the user of the machine, this guy here, is going to be doing the work input on the machine, right? He applies a force of 75 newtons over a distance of 5 meters. 75 times 5 is equal to 150, 300. It's going to be 375 joules of work input. On the other side over here, this is my work output. This is what the machine accomplishes. It lifts a 100 Newton box 3 meters in the air. So my work output is going to be 300 joules. Okay, go back up to my problem. Work input is 375. Work output is 300. Solve my mechanical efficiency, ME, equals 300 divided by 375. I actually have to get my calculator for this problem, which I have with me here. 375, excuse me, 300 divided by 375 equals 0.8. And that's times 100. I forgot about the times 100 part. Sorry, I'm getting sloppy here, which is equal to, once again, machine is also 80% efficient. Okay, hope that makes sense. It gets a little more complicated. I'm going to try a couple more. I'm going to leave a few of you to do on your own, but I do want to do another. Let's look at number 3. This is a different simple machine. It's not a inclined plane anymore. It says, using a lever, a person applies 60 newtons of force and moves the lever 1 meter. This moves a 200 Newton rock at the other end by 0.2 meters. Okay, and it wants us to calculate the mechanical efficiency. So, ME, WO, WI. Let's draw another picture. So if I do number 3 here, again, stick figure physics here. There's my person. My person is using a lever. Okay, I've got, what does it say I'm lifting? 200 Newton rock. Okay, so I've got a rock on this end. It tells me that the rock has a weight of 200 newtons. So of course, if you want to overcome that weight and lift it up, you're going to have to exert a force that's equal to the weight. Okay, and it says that the person applies 60 newtons of force and moves the lever 1 meter. So here this person is using 60 newtons of force and this lever goes down 1 meter. Okay, on the other side it says the 200 Newton rock is lifted by the lever for a distance of 0.2 meters. Okay, so this goes up a short distance, 0.2 meters. All right, so we can look here and see that I've got my work input on this side, which is going to be equal to my force times my distance. 60 times 1 is obviously 60 joules of work input. And on the other side, I have my work output is going to be equal to 200 newtons times 0.2 meters of distance, which is equal to, I believe, 40 joules. Let me do my calculation on here. Yep, 40, it's going to be 40 joules of work. Okay, I go to my problem. 60 joules of work input, 40 joules of work output. So I'm going to plug those numbers in, 40 joules, 60 joules. Okay, and it's going to be ME equals WO over W, 40 joules divided by 60 joules times 100, which is equal to 0.67 times 100, which is going to be equal to 67% efficiency. Okay, so there's that one. All right, well, I'll tell you what, for number 4, you've got a wheelchair problem. So you've got another ramp problem that you're going to have to do. It's going to be very similar to the one we did in number 2. All right, so if you need to go back and kind of look and think about what's going on, go back and review problem number 2. Problem number 5, okay, you have a lever problem. Okay, different numbers, but it's going to be very similar to the one we did for number 3. So if you need to go and take a look at number 3 and review how it was done, but I'm going to leave you guys to do those on your own. Okay, because I think you can handle it and that'll be good practice for you. I do want to go over number 6 together because I figure if I let you to try to do that on your own, maybe some of you would figure it out, but most of you would probably be confused. So quick look at this one. I'm going to start once again with ME W-O, W-I. Okay, if I read this problem, it says a pulley system operates with 40% efficiency. If the work put in is 200 joules, how much useful work is produced? Okay, so here's the twist here. It tells us right here the work put in is 200 joules. So that's my work input, 200 joules, okay? The twist here, though, is that it wants us to find the work output, how much useful work, which is work output, is produced. So it's asking us to actually calculate this, and it's giving us mechanical efficiency of 40%. All right, so this is using one of those sort of triangle deals where ME is on the bottom and then WO is over we, right? But we want to solve for WO in this case, right? So if I look at my triangle and I solve for WO, work output, it's going to be equal to ME times we, right? Because both of those are on the same level of the triangle here. So you multiply them. So let's plug in these numbers. 40%, when I plug it into my problem, is actually expressed, percentage is expressed as 40 hundredths. 40% is a number compared to 100. So 0.40, 40 hundredths represents 40%. I'm going to multiply that times 200 joules. Okay, so 0.4 times 200 equals, it doesn't make sense. Hold on a second. 0.4 times 200. Yeah, I guess that's what it is. Equals 80. And in this case, since it's work output, it's going to be measured in joules. That's going to be 80 joules of work. Okay, so that leaves you on your own to complete those two problems. Okay, and when you are done, this is going to need to be submitted to the assignment entitled Mechanical Efficiency. Okay, have a good day. We'll see you tomorrow.